Welcome to the lecture series of signals and systems. In the previous lecture, we have seen almost all the properties of the Laplace transform, and in this lecture, we will include some of remaining properties and some of the examples related to the Laplace transform. So, one remaining property is multiplication property or multiplication, or it is also called modulation property, or it is also called convolution in S domain, which states that if the Laplace transform of x1t is x1 of S and Laplace transform of x2 of t is x2 of S, it is given here if the Laplace transform of x1t is x1 of S, Laplace transform of x2t is x2 of S, then the Laplace transform of x1 of t into x2 of t will be equal to 1 by 2 pi j into x1 of S convolution with x2 of S. That's why this is also called convolution property in S domain. If the Laplace transform of x1t is x1 of S, Laplace transform of x2t is x2 of S, then the Laplace transform of x1t into x2t will be equal to 1 by 2 pi j x1 S convolution with x2s. We can find the proof of this function as Laplace transform of x1t into x2t will be equal to, as we know, it is limit from minus infinite to plus infinite, x1t into x2t into e power minus st dt, or by taking x1t is the inverse Laplace transform of x1 of S. So in place of x1t, I can put 1 upon 2 pi j integration from sigma minus j infinite to sigma plus j infinite and x1 of S e power plus st, or we can assume some other function in place of S. We can take it as dx1 of u e power ut du. This is the inverse Laplace transform of the signal xt, x1t. Because the Laplace transform of signal x1t is x1 of S, so it is in the form of inverse Laplace transform. x1t can be written in this way also. So now I will put this value of x1t in this given relation. So this will become Laplace transform of x1t into x2t will be equal to limit integration limit from minus infinite to plus infinite. In place of x1t, I will put this value 1 by 2 pi j integration from sigma minus j infinite to sigma plus j infinite x1 of u e power ut du, and remaining is e power minus st d. x2t is also there into x2t e power minus st d. From here we can change the order of integration and we will get the Laplace transform of x1 of t into x2 of t will be equal to 1 by 2 pi j, limit from minus infinite to plus infinite, x1 of u, x1 capital X1, this is capital X1 of u integration x2t e to the power. Now I will combine these two terms, e power minus st and e power plus ut. So this will become e power minus s minus u t dt, and whole integration of this is with respect to du. Now we know that the conversion expression for the Laplace transform, this will become, because this is the transformation of x2t in the s domain, but in place of s it is written here s minus u. So this is the expression for x2 of s minus u. Now this will become 1 by 2 pi j, 1 by 2 pi j integration from minus infinite to plus infinite x1 of u into x2 of s minus u du. And how this can be related to the formula of convolution of x1t and x2t, because convolution of x1s and x2s can be written as x1 u, or we can assume some different variable tau which is standard, into x2 s minus tau d tau, limited from minus to minus. Convolution can be expressed in this way, and we can relate this expression with this expression. Instead of, in place of u, the variable tau is given here. Almost this expression of the convolution relates to x1 convolution, x1s convolution with x2s. So this can be written as 1 by 2 pi j x1 of s convolution with x2 of s. It means that this is the Laplace transform of x1t into x2. Earlier we have seen that if the signals are convolved in the time domain, then they will be multiplied in the s domain. But here the second statement is, if signals are multiplied in the time domain, they will get convolved in the s domain. So here we are multiplying the signal x1t and x2t in the time domain, but what we are getting here is we are getting the convolution of their s domain signals. This is called multiplication or modulation or convolution in s domain property of the Laplace transform. One more property is conjugation property of the Laplace conjugation property of Laplace transform. This property states that if the Laplace transform of xt is x of s, then the Laplace transform of x conjugate t will be equal to x conjugate of s conjugate. Laplace transform of x conjugate t will be equal to x conjugate of s conjugate. We can prove this property. We know that the Laplace transform of x conjugate t will be equal to sigma, not sigma, integration from minus infinite to plus infinite x conjugate t into e power minus st dt, or this can be written as xt e power minus s conjugate t dt, taking the whole conjugate of this by taking the whole conjugate of the given relation, or this can be written as this inside the bracket, this can be written as x of s conjugate. So if I will put here x of s conjugate, this will become x of s conjugate its whole conjugate, and this can be written as x conjugate of s conjugate. So this is the conjugation property of the Laplace transform, which states that if the x of s is the Laplace of the x of t, then the conjugate of xt, Laplace transform of conjugate of xt will be equal to the conjugate x of conjugate of s conjugate, x conjugate of s conjugate. Now, so with this, almost we discussed almost all the properties of the Laplace transform. Some of them will be discussed when they are required. Now we will discuss some examples based on the properties discussed till now. By using properties, we will solve some examples to clarify the application of these properties. Suppose the first example says that we have to get the Laplace transform of, suppose xt given here is xt is equal to t u of t. This is based on the property differentiation in S domain, which says that if the Laplace transform of x of t is x of s, then the Laplace transform of t times xt will be equal to minus d by ds of x of s. Means if we are multiplying the signal in the time domain by this factor t, then signal in the s domain will be differentiated with respect to s. This is what the time the s domain differentiation property states. So we know that the Laplace transform of ut is the Laplace transform of u of t is 1 upon s. Then By using this property, we can say that the Laplace transform of t ut will be equal to minus t by ds of 1 by s. Or we can say that this is the differentiation of s power minus 1. So this will become minus 1 minus into minus 1 into s power minus 2. So this will become 1 by s square. This is called differentiation in S domain property of the Laplace transform. Similarly, we can use the time shifting property in this relation as it is given as u of t minus 3 Laplace transform of u of t minus 3 Laplace transform of u of t minus 3. We have to find the Laplace transform of u of t minus 3. So this example is based on the time shifting property of the Laplace transform, which states that if the signal xt has Laplace transform equal to x of s, then x of t minus t naught will have the Laplace transform e power minus s t naught into x of s. It means that if we are going to shift the signal in the time domain, then we have to multiply with an exponent in the s domain. If it is minus t naught here, this will be e power minus s t naught. If it is plus t naught here, this will be e power plus s t naught in the s domain of the signal. So here we know that the Laplace transform of u of t is 1 by s. So the Laplace transform of u of t minus 3 will be equal to, we will multiply with e power minus 3s in the s domain by s. This is the Laplace transform of u of e minus 3. The next is t xt given as xt is given as t into e power minus 3 ut. This example will include two properties of the Laplace transform. One is multiplication by exponential e power minus t in the time domain, or we can say that shifting in S domain property of the Laplace transform. Also, because t here multiplied, t is multiplied here, we have to differentiate the signal in the S domain one time. So this e power minus t ut includes shifting in S domain, shifting in S domain, and because of multiplication of this t, I have differentiation in S domain. I have to differentiate the signal in S domain. So first of all, we know that the Laplace transform of the signal ut, this is the first property states that shifting in S domain, if the signal xt has Laplace transform x of s, then e power minus at x of t will have the Laplace transform x of s plus t. Means if we are multiplying the signal in time domain with e power minus at, then we have to shift the signal in the s domain as x of s plus a. So from here we know that the Laplace transform of u of t is 1 by s. Then the Laplace transform of e power minus t ut will be equal to 1 by s plus 1. And because the signal is multiplied with t here in the time domain, it means that we have to differentiate the signal in s domain. And signal in the s domain can be written as s plus 1 power minus 1. And further, after differentiation, this will become minus of s plus 1 power minus 2, or this can be written as 1 by s plus 1 whole square. So this is another example which includes both the properties of the Laplace transform as differentiation in time domain, differentiation in s domain, and also shifting in s domain of the Laplace transform. One more example is e power minus 5t sin t xt is given as xt is equal to e power minus 5t sin of 80. This is another case of the time shifting in the Laplace transform, which says that this is not time shifting, this is shifting in s domain. As discussed earlier, if Laplace transform of xt is x of s, then the Laplace transform of e power minus 5t xt will be equal to x of s plus a. It means that we know that the Laplace transform of sine of 80 ut will be equal to Laplace transform of sine of 80 ut will be equal to a upon s square plus a square. So this will become a upon s square plus a square. So the Laplace transform of e power minus 5t sine of 80 u of t will be equal to, now in place of s I will write s plus 5. So this will become a upon a square plus whole square of s plus 5. This is another case of the time shifting in time domain of the Laplace transform. Now consider some more example, as it is given as the Laplace transform of signal x of s. The Laplace transform of the signal xt is given as s plus 1 upon s square plus 3s plus 4. Laplace transform of a signal x of s is given as s plus 1 upon s square plus 3s plus 4. And we have to find out the Laplace transform of x of 2t, x of 2t, second t into x of t, third. The third question is we have to get the Laplace transform of e power minus 2t xt, and the fourth one is x1 t convolution with x1 of t. This is not x1, this is xt convolution with xt. This is what we have to get by using the given relation. So we know that the first property states that the time scaling property of the Laplace transform means if the Laplace transform of x of t is equal to Laplace transform of x of t is equal to x of s, then the Laplace transform of x of 2t will be equal to 1 by not if it is a here. Suppose this is a general case, so this will 1 upon mod of a x of s by t. It means that we have to put in place of s, we have to put s by a in the expression of x of s. So this will become Laplace transform of x of 2t will be equal to 1 by 2 x of s by 2. And we know that the x of s is given as s plus 1 upon s plus 1 upon s square plus 3s plus 4 at s is equal to, I will put s by 2. In place of s, I will put here s by 2. So this will become 1 by 2 into s by 2 plus 1 upon s square by 4 plus 3 by 2 s plus 4. Or this can be written as s plus 2 by 2 upon, this will become s square plus 6s plus 60 divided by 4. Or this can also be written as, this will become 2. So this will be equal to 2 into s plus 2 upon s square plus 6s plus 16. This is what the value of x of 2t. Or this may be written as the next one is differentiation in S domain property of the Laplace transform, which states that if the xt has Laplace transform of x of s, then t times xt will have a differentiation d by ds in the s domain. So to get the Laplace transform of txt, we have to differentiate the signal with minus sign here. This signal s plus 1 upon s square plus 3s plus 4. We have to differentiate this signal once. So this will become minus d by ds of s plus 1 into s square plus 3s plus 4 power minus 1. So I will consider it as it is first function and this is second function, and we can differentiate this given relation by using the formula first function differentiation of second function plus second function differentiation of first function. So this will become minus of first function means s plus 1 differentiation of s square plus 3s plus 4 power minus 1 plus s square plus 3s plus 4 means second function differentiation of this s plus 1. Further, this can be simplified more as minus s plus 1 into s square plus 3s plus 4 power minus 2 and 1 minus sign will come here. This power will come outside and this will become power minus 2, and once again this term inside the bracket will be differentiated with respect to s. So this will become 2s plus 3 plus now this will become s square plus 3s plus 4 power minus 1 into differentiation of this will be equal to 1. And further, this can be written as s plus 1 into 2s plus 3. Now open the bracket and this will become s plus 1 into 2s plus 3 upon this s square plus 3s plus 4 s square plus 3s plus 4 its whole square minus this will become 1 upon s square plus 3s plus 4, or this can further be simplified as s plus 1 into 2s plus 3 minus this will become s square plus 3s plus 4 divided by s square plus 3s plus 4 whole square. And further we can multiply these two brackets. So this will become 2s square. This will become 2s square plus 3s plus 2s means plus 5s plus 3 minus s square minus 3s minus 4 upon s square plus 3s plus 4 whole square, or 2s square and minus s square. This will become s square. This 5s minus 3s will become plus 2s, and this 3 minus 4 will become minus 1 upon s square plus 3s plus 4 whole square. This is what we will get if we multiply the signal in the time domain by s. So if we multiply the signal in the time domain, then the signal will be differentiated in the s domain and we will get this result. So this is all for this lecture. In the next lecture we will include some one or two properties are left of the Laplace transform, like initial value theorem and final value theorem, or we may use the Parseval's theorem of the Laplace transform. So we will include some more properties, one or two more properties, and many We have to discuss some more examples in this context, so we will include these examples in the coming lecture. So thank